Hello, hello. Welcome to another episode of Good Garbage podcast. And I'm super excited to have a hero of mine, in a way, Oded Shoseyov, join me today. Thank you, Oded, for this opportunity to talk to you. You do know I'm a big fan of yours, so I may have some nervous moments. If I do, please
Mhm.
forgive me if I stumble anywhere. So, Oded, of course, again, a person who needs no introduction, but I will do a little bit of justice. Oded has been creating materials for a while, 30 years or 32 years now, Oded, right?
Who
Out of
counts?
which, yeah, something like that, and I'm sure you will clarify that. 62 patents, the last I saw, uh, part of 14 companies, or founder of 14 companies. A title that has been given to him is the man who just can't stop inventing. And so my story with you, Oded, and I don't know if we shared this when we met in Jerusalem. Um I obviously listened to your TED talk, and if anybody is in the material space and hasn't heard your talk, they must. And I was totally blown away. You know, the whole idea of nature's inspiration and creating materials and the actual materials that you've been creating. And of course, we've been in touch through Melodia, and it's just amazing what your company there is doing. And you don't know this bit. My father passed away because of a heart failure due to his valve not working after 15 years.
Oh,
So
I'm
before
sorry
they
to
could
hear
even
that.
change the valve, it just lost. So it is a personal, it was a very personal journey for me as well when I heard you talk on that specific subject as well. So for the listeners, I heard your talk and I tried to contact you, but of course with 14 companies and the amount of work you do at the Hebrew University, it was so difficult. But I finally managed to do that, and I just like again, you may not know this, but I took literally a flight the next week as soon as you responded, and I said, okay, I have to go to Israel to meet Odette, and what a meeting
Wonderful.
that was, and I've learned so much from you. So this is going to be a learning session for me, Odette, probably a master class, and I welcome you and thank you so much for joining into this talk. Just to inform you, good garbage. The idea behind good garbage is that, and this is something close to your heart. So the idea behind good garbage is that how do we build regenerative packaging at scale? So, we can all create little, innovations, but till you can't scale, and this is something you've talked about a lot, it doesn't work. The big changes will only happen that way. So I'm basically trying to talk to innovators, scientists, creators, disseminators of materials so that we can learn more and enable other people to learn more. So that I'm going to jump in now and ask questions. You can stop me when you want. You can take it the direction you want. This is all you. So for me, and I always start with this question, because it's so important when we think about materials. So, can you think about your earliest memories as a child about packaging, and how did that influence you? And how did that take you on your journey, which has obviously gone in many, many directions?
So, when I say packaging, for me, I think the earliest memory and probably the one that um, somehow dictated my career later on was uh, I was born to a family of farmers. My father used to grow vineyards, and at a certain point of time, we had table grapes. And as a kid, when everybody, during summertime used to go for campings, I used to go to help my dad in the vineyard very early in the morning. It was like 5 a.m. In the morning, starting to harvest the grapes. And my role was to fold the cartons,
Uh-huh.
the cartons that we used to pack the grapes. So I think that if you tell me the words of packaging in childhood, this is the first thing that comes into my head. um, And I think that over the years, when I saw how hard is agriculture on one hand, but on the other hand, um, I was always impressed by my father's love to the plants, to be there in the vineyard. That I knew that I really want to go, after graduation and high school, and in Israel we also have the 3 years army. I really wanted to go to the university, study agriculture, and go back to work with my dad in the vineyard, and just to get some knowledge and help to improve things.
Hmm.
But long story short, I ended up at the university, never came back to the vineyard. But I think that really the time that I spent those days understanding how sustainability is so important,
Yeah.
not just for agriculture, but actually for our life, brought me very, very quickly to the understanding that we really need to do things differently.
Yeah. Wow.
Uh,
But you did. So just a follow-up question on that. You did study winemaking, and that, and then and the follow-up question is that how did that transition into being nanotechnology and all the other things that you do? So you study winemaking, and then you go ahead and do various things from there. So how does that connect?
so actually, it all started in the last day of my undergraduate studies. Just when I did my bachelor degree in agriculture. I was walking in the hall, and I met who will become my supervisor, and he was Professor Benami Bravdo. That I took one of his courses in viticulture, and he asked me, "What are you going to do?" So I said, "I'm going to go back to my dad, to work in the farm." So he said, "Why don't you come to do your master's with me?" So I scratched my head and I said, "But I think that the bachelor degree is enough to work on a tractor." uh, They said, "No, no. I mean, there are still a lot of things to learn." So I decided to to give it a chance. And first time I got into the lab, I realized that I'll never leave this place, because
Wow.
it really brought me back to childhood. When you go, it's like you're in Disneyland,
Yeah.
and you
Yeah.
have now the possibility to play and to really play with nature,
Yeah.
and find new things. And I followed his supervision, and my PhD was in fact on biochemistry of wine
Hmm.
flavor. And I remember that I kept asking him, uh, what do I have to do to become a professor at the university? Because that I knew I really wanted to do. He said, "Well, the first thing you have to go to do a postdoc. Better do it in a good university. But then make sure that it's not going to be something that you did already. Don't follow your PhD. Just do something totally different
New.
and innovative, new, something that is really new." So I kept asking myself, what is the next thing? And remind you, this is 1987,
Uh-huh.
early days of molecular biology and protein engineering. And I didn't know anything about it, but I realized that it's fascinating. And so I was lucky to get accepted to do my postdoc at UC Davis in California, in one of the best protein engineering labs. 3 years later, I got my position at the university, so he was right. uh, and then for some time, when I was working in the department, I was still looking for my new way. And when the Nano Center was established, I always give credit to our former president, Shimon Peres, who was really a visionary. And about 20 years ago, we went to the government, and he said to them that Israel have to invest in nano centers. And he was able to convince the government to put $500 million in 5 nano centers. So each university got $100 million, which was a lot of money that time.
Yep.
5 universities to establish a nano center. And again, I remembered what my supervisor at the time told me. Always look for the new things.
Mm-hmm.
And I didn't know anything about nanotechnology at the time. But admittedly, nanotechnology was still being dominated by inorganic chemists, physicists, very few biology. So I came to the Nano Center and said, I'm going to take, the lead on nanobiotechnology. So what is nanobiotechnology? I said, I'll find that. We'll find together.
We're still figuring it.
Yeah, and sure enough, already those days, when I thought about it, I said that nanotechnology was actually invented by nature. It's we human being just playing a very a small role in this game, and for a simple reason, because in nature things are built by themselves. I mean, everything is self-assembled, and these are the principles of nanomaterials, that they self-assemble.
Yeah.
And very quickly I found out that you can find really amazing materials in nature, in the plant kingdom, insect kingdom, in any kingdom. And in fact, they are so much better than everything we do. Just remind me, it's something that happened to me last week.
Uh-huh.
I have one of my students, she is working on nanocellulose. I'm sure we will talk more about nanocellulose. Yep. And she's taking nanocellulose and make different cellulose films with different methods, and we measure their piezoelectric properties, which means that you take this film and you press it, and it generates voltage. Okay? So you can generate electricity from that. There are a lot of applications for piezoelectric materials, for sensors, for you name it. And we published a few years ago that nanocellulose has piezoelectric materials, piezoelectric properties. Mm-hmm. So we try to improve it and then I think you're going to love this story. Last week she came to me and said, listen, I found really an amazing paper that came from Delhi, from India. There was a guy there that he also tested the piezoelectric properties of biomaterials. And if you read the paper, it says the following: I went to Delhi market, uh-huh. And I bought a pomelo, citrus.
Yeah.
Cut it, took out, and then within the pomelo, when you cut it out, there is a white skin. So he took this skin, just the skin, dry it, and tested its piezoelectric property. What he found out, that when you press it, he got 10 times more voltage than what my student was doing with very sophisticated nanomaterial that she prepared. And so that really, if you think of it, we're trying to make piezoelectric materials.
Yeah.
I mean, the industry makes them from ceramics, and they use, temperatures like 1,000 centigrade to make these special ceramics, and it's brittle and sensitive and so on. We take nanobiomaterial, we try to assemble it. Okay, it's biodegradable, it's compostable, but we invested a lot of effort. This guy went to the market, took a pomelo, ate the pomelo, I guess, in the lab, and from the remaining, he got a piezoelectric material which is 10 times better than everybody else. So just to say, I mean, this is, he said, this is garbage. The garbage.
Yeah.
This is
Yeah, yeah,
better
yeah.
than
That is thrown
garbage.
away.
This is better than the original.
Yeah, yeah, yeah. So just for my learning and clarity, is when we make even pulp and paper, we usually check the charge balance and whether it's cationic or anionic, and we do our chemistry accordingly. So
Yeah.
is that also to do with the natural charge? And we call it the God energy, right? If you look at a piece of paper, there is no weaving, there is no, there is no addition, and it just stays together because of that charge balance. Is that something to do with the fiber addition, something to do with that charge and how it plays? And of course, when we supply to the medical industry, for example, they want to make sure there is no charge in the
Yeah.
paper. So we have to make sure that the chemistry, again, has no metals, etc., etc.
So, admittedly, we don't fully understand. We don't fully understand how the piezoelectric properties works in nanocellulose, and particularly in composites. But I assume that the natural charge of the fibers, has something to do with that. But it is something that we are still learning. But imagine, in the future, if we will be able to command it, if we will be able to control it, you could think of really packaging that when you just touch it, you want to grab it, you generate some electricity that can do something.
Yeah.
For example, can maybe show you a display, or maybe send a signal to the cashier or to whatever. So there are a lot of interesting applications in materials that you wouldn't even think that they could be generators of energy, of
Yeah.
electricity.
Yeah. So I've loved your ideas in your talks, both your TED Talks and otherwise. You always reference the sequoia tree, and it's so amazing, and any tree for that matter. And for me, what has been very interesting is this whole photosynthesis mechanism where the tree takes carbon from the atmosphere and creates cellulosic fibers, sugars. And of course, there are some minerals that are taken from the ground, but it's fundamentally carbon from the air. Whereas when I look at, our processes, they are all heat, beat, treat. We take the cellulose, we smash it up, and we take out all the lignin, and then we try and create something where the fibers bond. So do you see a future where we as humans, instead of cutting things and making things, and which is what you've been doing, like trying to avoid that, can actually even make sugar-based fibers, ideally from thin air, or a more additive process instead of a subtractive process?
So I am positive that in the future we will be able to do things like that. Simply because today genetic engineering of plants is becoming a more and more common practice. And more specifically, technologies like genome editing, like CRISPR-Cas and so on, that really introduce new and rich toolbox to geneticists, and so I think it is very likely that in the future we will be able to engineer plants that will be more suitable for certain packaging materials.
Yeah.
And we may, at the end of the day, cut the tree or still do some processing, but I think that most of the bleaching processes that we're using today will be avoided because it will be much more suitable for the material that we want to, or the product that we want to make out of it. And in addition, I think that we will find in the future other sources of materials. I can share with you that I'm today also working with an Israeli startup that found a very elegant way to make a biocompostable plastic.
Okay.
Packaging for many applications you can use the paper, but there are still some applications that thermoplastic processing may be required. And yes, we have today, PLA, polylactic acid, but admittedly, it's not the best material. First of all, its melting temperature is very, very high, so you have to invest a lot of energy. And the most problematic thing about PLA, as far as I'm concerned, that it competes with food, because you start from corn and sugar, and so in a world that we have to think about how to feed the population, PLA is probably not the best solution. What they found out is a very interesting way to take regular seaweeds, just seaweeds from the ocean, and take these seaweeds and use that to feed halophilic bacteria. These are bacteria that really loves salty water, and they know, these bacteria, how to convert the sugar into a thermoplastic biocompostable polymer called PHBV. PHBV has been known for some time, but it's a wonderful thermoplastic material with relatively low melting temperature, can tune the properties, and unlike PLA that you have to, if you want to recycle it, you have to take it to the factory. This PHBV, you can put it in your composter, and a few weeks later, it's gone.
It's upcycled.
The only problem is that it costs a lot of money. But they, I think, came up with a very interesting idea to take very inexpensive seaweeds. On the one hand, they don't compete with anyone on these seaweeds. In addition, the seaweeds also, they make photosynthesis, so they absorb carbon dioxide from the atmosphere and from the water. And in addition, we still have much more ocean than land. So I think that these materials could be also very useful packaging materials for us in the future. Materials like PHBV that is produced from seaweeds and halophilic bacteria.
That's amazing that you mentioned that, because I was doing my master's in biomimicry, and of course my whole focus was how do we find better packaging. And one of the things that I got truly influenced by was sea kelp or seaweed. And the interesting thing there, and I don't know if you've explored this, but sea kelp, you could have, huge storms in the ocean, but it just has this elasticity, and it moves and it sways and it sort of stays. And it's beautiful because what we found was that when we are manufacturing, it's the same thing, it's cellulose ultimately. And when we are manufacturing pulp and paper, typically our processes align the cellulose at about a 25-degree angle. In a sea kelp, it is 60 degrees. So
Wow.
that's the main difference, which was very interesting because just by reorienting the fiber, it was possible to create huge elasticity. So it's interesting that you mentioned that. I don't know if you can throw more light on that and educate me if you know more about that idea.
So I don't know much about I don't know much about the elasticity of seaweeds, but what you're saying, first of all, makes a lot of sense. And I think also that the sea world is really can give us some really amazing things. I mean, it's a undiscovered world yet. Last Thursday, I had a tour with a professor from Tel Aviv University. She is an ecologist, and she approached me some time ago, and she said that she's specialist on a special kind of animal, a sea animal, which is called tunicate.
Hmm.
Tunicates are really small creatures. It's an invasive species. They grow all over the world, and it has two holes.
Okay.
From one, it sucks the water, and the another one, water goes up. They typically, if you go to marines and to ports, they attach to ropes and
Aha,
to
yes.
yeah. And it turns out that in Korea, they eat it, and in fact, in the Second World War, they said uh, that this was their staple food. They just take it out from the sea, cut it, and eat the inside. It contains a lot of antioxidants, and it's really very healthy, and it's a good source of protein. So she approached me and said, "What do you think? Can we grow it in, as a protein source?" So I said, I don't know anything about tunicates except that for someone who's been working on nanocellulose, I know that some people in Canada explored the properties of nanocellulose. It's actually the only animal that makes cellulose.
Hmm.
Because cellulose typically is made by plants,
Plants, yeah.
and it's the tunicate is really is the cover. Okay,
Hmm.
it's made of nanocrystalline cellulose, and it's like a really strong shell that protects the animal inside. So if you think of it, it's an animal that lives in a wood. But this particular nanocellulose is actually has the highest aspect ratio ever
Hmm.
found. Like for example, if regular cellulose nanocrystals from plants is about 100 to 200 nanometer in width,
Yeah.
and 5 to 10 nanometer in the length, and 5 to 10 nanometer in width. Uh, this one is more than double the length.
Yeah.
So on Thursday, I went with her to Jaffa port, and we collected some with my students, and we are going to study this. Uh, and I think that this is, and you hold it. I mean, it's really strong. So think in the future, people will be able to grow it, for food. and so you can use the inside as the protein, and the outside tunicate, which is cellulose. You can make wonderful packaging materials. It's a very strong material. It's like
Yeah.
almost 100% nanocellulose, crystalline
Yeah.
nanocellulose.
Yeah. 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 I can think of two more sort of ideas from there. And of course, I'm sure you're familiar with these. I know that the Weiss Institute used chitin and again from spare shells, and they
Yeah.
created some films. I did talk to them, and they, at least what they informed me then, was that it wasn't possible to scale it up. So that was their challenge, and it was interesting, very similar to what you're talking about. And the other one, which I studied, and again, I would love for you to throw some light on this. So, and it'll also take us towards nanocellulose and films, that direction. So I was looking at, so the passion for me has been that of flexible films, and how do you create structures in order to have the multi-layered kind of metallized films, become different. And I've so we were looking at different barriers in nature, and air barrier was also becoming an issue. So we were looking at this, and we found that the Alaska pollock fish, because of the cold temperatures, has excellent oxygen barrier properties. But then, how does one take that gelatin, basically, and you talk a lot about collagen, and how does one take that protein, that amino acid, and then create it? So the two questions is, how do you see that translating? Like, okay, I've found this inspiration. It's amazing. Of course, it's evolved over time in certain conditions. But now I want to take this and maybe microbially multiply it. That could be one method. And then how does one scale it up and apply it? How do you see that evolving?
So I think that first of all, it's very interesting that that the proteins also have oxygen barrier properties. It probably has to do with the fact that gelatin self-assemble. Okay, on one hand, but in addition, on the other hand, it has a lot of hydroxyl groups. So OH, yeah.
Yeah.
And we know that good oxygen barriers like nanocellulose or PVOH, they have a lot of hydroxyl groups.
Yeah.
But the trick is not just the presence of hydroxyl groups. You really need to have this very intimate collating polymer structure, so that when the oxygen try to go through, he will have to go through tunnels and really have good chance to hit on hydroxyl groups that will form hydrogen bond and retain the oxygen. So I think that assembly is one thing that need to be considered. As far as a production, then again, I think the plants or in the future maybe seaweeds can definitely produce for us all these proteins in copious ways. I mean, I am, of course, most of my work is in plants, because in plants the expression systems in agriculture is more advanced than in the sea. But I am sure that people will find out ways to produce valuable materials in engineered seaweeds in the future.
And when you say expression mechanism, what does that mean? When you say plants have a better expression mechanism?
Expression means, for me, it means that I get a gene from insect and I stick it into a plant, and now the plant express this gene, which otherwise, this gene is not found in plant, like collagen that we've done.
Yeah.
For example, plants don't make collagen, but now when you have technology, you can express collagen gene in a plant.
So
That's what
let's
I have.
let's yeah, sorry, let's go take that a little further. For those who don't know, you took collagen and put it in a tobacco plant and grew that, and of course you could do numerous things in the medical field, especially with that.
Yes.
So why tobacco? What was it about tobacco that you used that plant and no other? Or I'm sure you experimented with many others and chose tobacco.
So, several reasons why they decided tobacco. First one was because when we produced human collagen in plants, our aim was to use the collagen for medical implants, or injectables for human being. And the FDA prefer that if you are going to introduce human gene into plant, prefers that the plant will not be in the food or the feed chain,
Okay.
for safety reasons. And obviously, tobacco is not edible by plants or by human or animal. But there is another reason, and that is if you are going to produce your protein in a annual plant, like potato, for example, then you'll have one season. At the peak of the season, you have lots of potatoes done. Now your factory can process it for the entire year. So you have to store it and so on. Tobacco, we can grow four cycles a year, all year round. So we can supply to the factory the fresh leaves every day, every day. So production is more homogeneous, and it's much easier.
Makes sense. Yeah.
So these are really the main reasons.
Okay. Uh, so I was talking to my dear friend who you may know as well, Gavin McIntyre from Ecoative, who created a lot of stuff from mycelium. And he said a very interesting thing, which is something that you, in passing, also referred to. And you talked about seaweed, and he again mentioned similar things. Like the idea for me, what has been fascinating is this whole field of microbial multiplication, bacterial kind of multiplication. And since I heard about that, it's just been this thought process that can one really grow packaging? Instead of growing, of course, we grow leather and we grow meat now, and things like that. But everything in nature is packaged and so beautifully packaged. So if I look at, say, a
Mm-hmm.
corn hull, can I take that corn hull, which is such a beautiful structure, and can be so good because it's so structured so well as a packaging material, and then create multiples of that? So how do you see that happening if you do? And then how can that be done at scale? Do you see that as a process that would happen in the near future?
So, first of all, I think that it can be done at scale. Eh, um, and the way that I see it happen is that we need really to combine between cellulose, which is hydrophilic, on one hand, to other materials which are more hydrophobic. So we'll be able to enjoy both the oxygen barrier strength on one hand and water barrier properties. So I can envision in the future technology where you have think about a frame, okay, like a reel to reel that goes into. They have like a matrix that goes into a bath. That in the bath maybe you have something like a gluconobacter that can produce a bacterial nanocellulose, okay, and it goes from there, and it grows, then goes into another bath that actually now takes the bacteria, okay? And then it goes to another bath where you have some kind of filamentous fungi that grows on that and provide the water barrier,
Wow.
and it goes out, dry or mold it, and dry it as a mold. I mean, it's I'm sure that it can be done. It's the principles are there. What we have to do is to take the building blocks and do the right engineering to make it happen. And you could even think of even more advanced things like today we have, for example, bacteria that makes carotenoids. The red carotenoids, and of course orange and all these colors. So you can even paint it, with
Yeah.
this bacteria. And because they're the carotenoids are antioxidants, so they're pigments, but also protect from oxidation, and everything is sustainable. Everything you can actually eat it probably. We just need to look how things are done in nature and try to mimic that rather than reinvent the wheel from where our building block is fossil oil, which is not really sustainable.
Yeah, that takes me to an amazing quote of yours where you actually said that, and this was again music to my ears. I think you ended that talk with this idea that we will not switch to we will not come out of fossil fuels because fossil fuels run out, but because biomaterials will be better, which is so
Exactly.
fascinating. And that's such a positive, optimistic viewpoint, because otherwise we think that, okay, this is a non-renewable resource, so eventually it's going to run out, and that's a poorer future. You're talking about a richer future with better materials, which is amazing. And your what you're talking about right now makes so much sense as biomaterials evolve. So, just for my understanding, and I'm sure a lot of listeners' understanding. So, coming back to just the example of, say, the corn hull, and that's just as an example, how would you go about deconstructing it? How would you go ahead and determine exactly what are the contents and what is the quality of that content? So if it's all cellulose, what is it and how is the fiber structure? Is that easily possible with the technology today, or is that still evolving?
Well, it depends. I mean, first of all, if you talk about the corn hull, I'm sure that with the current technologies, we can we can definitely study and pretty much analyze each one of the components there. The question is, what do we need to learn from that? I mean, so see, I assume that the structure of this corn hull is such that it's perfect for the corn. Once we try to use it for something else, we may have to compromise on something. Okay, because most probably what we want to pack it with is no corn. Doesn't have the properties of corn, doesn't have the requirements of corn, and maybe the shape of corn. Maybe I want to pack an iPhone with that. So what I believe we should do is just try to really understand the principles in which nature uh, protect things, like the good example you gave. And just use these principles to do better engineering of the packaging we make. I'm not expecting, well, maybe in the future, but I'm not expecting a field that will grow packaging material. It will be the size and the shape of the smartphone. It could be nice, but maybe it's not that necessary.
And you
But
would be taking land away, which is
yeah,
another
yes,
challenge.
yes. But think about what I just told you before. This factory with a reel-to-reel system that you have. You can create a material, and this material is going to be a film. It's still wet, so you can mold it. You can do whatever you want, and it will be like it's like a paper mill. That downstream will be the converter. The converter will take this from the reel and will do what it wants. Okay, if you want to make a packaging for a smartphone or a packaging for fruit, you will do it. By the way, I think that in the future, and that is what I wish, that the packaging will be so thin and so effective that you won't even see it.
Wow.
That I can think of things like that. Like imagine today when you have cornflakes or muesli, we have a carton, okay, and inside we have a laminate. The laminate is there to protect it from photooxidation. But in fact, the carton already does its job as far as a UV light. Now we need just to give it an oxygen barrier. So if you take all these cornflakes, and the raisins and the almonds, the nuts there, and you coat it with a film of nanocellulose.
Yeah.
There is only 500 nanometer film thick. You don't really see it, but
Yeah.
it provides all the protection you need. Okay, because oxygen is not going to penetrate. So you don't even need the laminate. It will
Yeah.
be only in the carton.
And it probably provides a little more fiber to your body.
Yeah, of course.
So what I see again in this, and this is something that I've been fascinated by, and I'd love for you to throw more light on this. So when we look at nature, all packaging grows with what is inside and dies with what is inside. So in a way, the way nature is created, and of course, it has all the other. It'll give you an expiry date by wrinkling, and our skins and everything else around us, and it has all these indicators whether it's good, it's not good. Um, but the challenge that I find is that the way nature has done things is basically till it's alive, the packaging is also alive. And once the substance dies, the packaging dies as well. So in a way, what you're saying makes a lot more sense, that you can't just take something and say that I'm going to adapt it, because that's going to be the other challenge if it's alive. So you have to take the idea and then adapt it to packaging. But would love to hear your thoughts on that.
No, I think you said exactly what I mean. That we need to learn from nature, but and understand the principles, but not necessarily do exactly the same, because we we are manufacturing things differently. We you see what's going on these days with alternative proteins. That people start to make cultured meat texturized vegetarian proteins. So I think that we will have um, factories and manufacturing processes where we process um, either vegetable proteins or other things to products. Okay, and these products need to be stored somehow, packaged. Uh, but the packaging could, so it's not, what I'm saying is that we need to study and learn from nature, but not necessarily do exactly the same. Okay, there are also some good ideas that a human being came up with, and we shouldn't just give up on them.
Yeah, yeah.
And one good example is there is no animal that reached the moon from Earth. Well, but man was able to do it already in the 60s. So, you know, uh, maybe wasn't such a good idea, but but this is another thing to argue. But what I'm saying is that a human being can be still innovative beyond what nature does. But on the
Yeah.
other hand, you can say that we are also part of nature. So the fact that we got to the moon was it was because
Part of
we're
that.
natural.
Yeah, but closer to even if we look at the plastics that we've created, that's such a magic material in the end. Okay, we have a different problem of disposal, but if you look at it, and if you look at flexible packaging in particular, it's ultimately it was a waste product from petroleum, and somebody, and I
Yes.
haven't looked enough in it, I know that the famous guy who created it about 70, 80 years back, but the whole idea of the barriers, because today we open a bag of crisps maybe 6 months from the manufacturing date, and it'll taste as good as yesterday, right? So of
Yeah.
course, it's human ingenuity, and we can, like you say, like we have to create better materials. It's not about running out of fuel. It's about evolution and creating better biomaterials, and that takes me to two more sort of thoughts which I would want you to, and of course, you can comment on what I said, but um, the two thoughts that came to me before was this whole domain that you've been exploring of DNA sequencing and multiplication. How do you see that playing in the process of building packaging materials? Let's start with that, and then I'll go on to the next one is around barriers, but I'll go on to that afterwards.
So I think that it plays a major role, and it really connected to your comment before, which I totally agree. I mean, thermoplastic materials and of course, all the extrusion technologies and all that are really amazing manufacturing technologies. The only problem is that the materials that were picked probably were not sustainable and problematic, but the concept is amazing, and we should continue to do that, but with biodegradable, compostable thermoplastic material. So that's one thing. And this is really, but our ability to do it effectively really relies on your second question, which relates to DNA synthesis and sequencing, and that's revolution. I mean, it is a revolution, and I can tell you that when I was a postdoc, I remember that we used to do the sequencing ourselves. We had to build this big gel. And it was very, very slow. I mean, it took me 1 year to sequence a single gene. And it was amazing at that time. Today, you take a DNA, you send it to the lab, and you get the sequence the next day,
Wow.
and you can sequence the entire organism for very small money. The price of sequencing dropped dramatically, so that's one thing. But also the DNA synthesis. You know, today, when a student of mine needs to, to synthesize a gene, so he's just doing, the computer, the design, and send it to the company, and a couple of weeks later, you get the gene back.
Amazing.
And in fact, because it is so cheap, he's not just synthesizing one. He makes 30 versions of that.
Wow.
And so the technology it's this, because of the advances and because of the affordability, we can improve on production systems, natural production systems like bacteria, fungi, yeast, plants, of course, seaweeds, and so these are going to be our manufacturing plants, not fossil oil chemical reactors.
And they will be able to build different sequences to enable different materials.
Everything. In fact, the future is that in the future you will be able to put on your computer what are the mechanical properties that you wish to have in your material, and the computer will tell you which polymer you need and where to produce it, and if you need to modify the chemical nature of that molecule, it will suggest the DNA sequence that you need to change for the organism to make what you need.
Wow,
and it's not like something that will happen in 20 years. This is going to happen in less than 10 years from now.
amazing.
People are working on that already.
Yeah, I actually went to the Ginkgo Bioworks lab and I was blown away. I'm sure you've visited or known about them. But yeah,
Yes.
stunning. The amount of equipment that they were investing in, the kind of work they were doing in this whole DNA sequencing space was so stunning. And I hope that I'll be able to get someone on this talk to learn more from them as well and see how we can move further. So you and I, of course, have talked in the past about barriers, and that's something, and that takes me to the idea of nanotechnology and all that you've been doing with Melodia, and it's so beautiful to see that work continue to evolve. So just for the audience sake, so earlier the way we would create nano crystalline cellulose was basically by a lot of mechanical grinding, which meant huge energy. And then, of course, I managed to visit your lab and saw that you would do it so differently through chemistry. So we'd love to hear more about that, and also how you see, because the challenge that we face today, and I'm sure you hear about it enough, is ultimately the difference in cost. And how do you see that coming down so that we can get the right barriers in order to be able to get the right moisture and oxygen, off and create better biomaterials?
Yeah.
And I'm sure you think about this every day, so love to hear.
So, first of all, as you mentioned, there are many different ways to make nanocellulose. What is unique with the technology that we developed was we simply looked at each one of the processes that on one hand you need to hydrolyze and get rid of the amorphous regions of the cellulose on one hand, and once you end up with crystals of the nanocellulose, you need to recover it in a cost-effective way, and what we have been able to do is for each step to introduce very effective recycling systems. So very little waste comes out, and also the acid that we use, we actually recover it again and again and again in the process. Um, as far as the cost goes, I think that just like any technology, the cost is driven by scale and
Yeah.
location. Scale and location. And what is unique about the technology that we developed at Melodia is that it is very suitable method to be integrated into pulp mill,
Yeah.
because the pulp mill has already inputs and outputs that can serve the nanocellulose production. Um, and so I believe that in the very near future, cost of production of nanocellulose will drop dramatically, which will make it will make it feasible for even very simple products. By the way, already today, if you want to make flexible packaging, which is 100% paper based, okay, no aluminum, no polymers, no plastic, nothing, at a competitive price, you can. It's already
Wow.
there. We are already there. Um, eh, and I think that the industry will dictate basically this change, and it's happening because, as I'm sure you know, Nestle, which is probably one of the largest food manufacturing companies in the world, they made a declaration
Yeah.
that in 2025 none of their flexible packaging will be made of polymers. So this is a very, very strong statement.
Yeah.
And the only way to make such a statement is that you look at the technology and say, hey, it's possible. It will take some time, but it's possible to do it. And this is what's going to happen. There is no way back.
Hmm. And do you see both water vapor and oxygen barriers coming from the same nanocellulosic substance, or do you see a different structure?
No, it's different structures because it's okay. At least what we at the university and in Melodia developed was it's actually two different coatings. Of course, everything is bio-based, but oxygen barriers uh, inherently comes from nanocellulose, but water barrier is more from fatty acids. Yeah, just like plants. You know, in
Yeah.
plants, the cuticule is is not made of cellulose. It is
Yeah.
made of waxy material.
Yeah.
And
And how do you, so the other challenge that we see is that ultimately you have to try and use the same supply chain because you can't disrupt everything at the same time in order to go to scale. So one of the challenges that comes with that is heat sealability. So does the nanocellulose manage that, or do you have to give another layer for heat sealability?
for sealing, some of the water barrier can provide that, but otherwise you can. There are solutions for that as well, which are another coat, which enable the sealability. Yeah.
That's so wonderful to hear that you are already seeing it actually happen at commercial scale. And you're absolutely right. An integration with pulping, and I'm sure you guys are looking at it, would enable it to scale significantly and then be able to change that whole material
Yeah.
space. So yeah, so super excited about that. One sort of towards taking it towards closure, and another very interesting material that I came across recently, and I'm sure you've heard of it, is this whole idea of using minerals, and it's called stone paper, for some example. It's not really paper, but using calcium carbonate and integrating it with HDPE initially, but 20 to 30% HDPE, and then making pellets and blowing it up in regular extrusion technology. Um,
Yeah.
what again, you can, I'm sure there is a way to replace the HDPE part through a biomaterial. And maybe even if you can't do it with 20%, maybe 30 or 40%, you still got 60% waste minerals, and then you put in a biomaterial and again take it to a technology which is the same supply chain. You make pellets and you put it into the extrusion cycle, and people can make
Yeah.
bags or whatever. So how do you see that evolving? And do you see a particular material that would be able to substitute high density polyethylene?
Yeah, so I think that essentially it goes back to what we discussed before with bioplastics like PHBV, which I believe can be modified to replace high molecular weight polyethylene at the end of the day. It still requires some more research, obviously, but I think it is possible. I would refer you to one of the papers that we published because and the reason I say it is because when people talk about high molecular weight polyethylene, materials like Dyneema and so on, which are really very 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 strong plastics. We've published a couple of years ago a paper where we actually made a composite of nanocellulose with a PVOH, and we were able to achieve a toughness of 200 megajoule per cubic meter. Just to give you a feel, Kevlar, which is very strong fiber, is about 50 megajoule per cubic meter. Achilles tendon, which is the strongest material we have in our body, is about 7. Spider silk, which is the strongest material ever, natural, is 150. Combining PVOH and nanocellulose is 200.
Wow.
So it doesn't have to be one material, but composition of two interesting materials they complement each other, can end up with very very tough materials. So and toughness is of course the energy to break. So it's really what you need.
Yeah, and that's very similar to nature as well, right? The building blocks may be few. It could be sugars and amino acids, and you could have a few minerals and a very small part of the periodic table, and voila, you get the
Yeah,
toughest materials and the most flexible materials, and it's
exactly,
those building blocks,
exactly.
which is very similar to what you're saying, and it's always
Yeah,
combination. And I even see, combination and sizing, like you're talking about nano, and then,
yes,
you have, and how do you create the building structure is something that is
absolutely.
amazing when you look at nature.
Yeah, I agree. I agree.
So, 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 I've been researching all you do, and it's amazing. How do you do what you do? Like 14 companies, uh, obviously research, being at the Hebrew University. How do you keep doing it? And it's so diverse when I look at the kind of things that you're doing in terms of, cultured meat, in terms of materials, in terms of wine. So how does Oded keep going the way he does?
So I think that the secret is to work with young people,
Aha.
uh, and to really uh, have the focus on the students, because they always come up with some really good ideas, and all they need is just a good guidance. Um, and this is one thing. The second thing is that keep keep yourself curious about things that go around you. Um, I really believe that we can do more than one thing. So just uh, continue to be curious about things around you, and work together as teams, and not just an individual. And by doing that, you can achieve a lot.
Yeah, wow, it's really amazing to read all that you're doing. So, just to take a cue from what you were saying in terms of young people, I know that you are invested in numerous companies, ideas, technologies. But apart from your own set of, investments and ideas, where do you see which companies or people are in the space that are inspiring you, or are companies that are inspiring you?
So I will answer to that like that. I was once asked by a reporter, why do I stay at the university? He said, you have a nice office, but I'm sure if you go to the science park with one of your companies, you can get a really nicer office and more space and so on. So I told him I will never leave the university. He said, how come? I said, because all the ideas, everything that I have comes from this spring of ideas.
Wow.
And he said, what is that? I mean, it's the young students. He said, how come? He said, because they think out of the box. He said, but why? How come they think out of the box? And I said, because they still don't know where the box is. And I really mean it. I think that
Yeah.
the more we learn, we become more and more focused, and we tend to throw away good potential ideas.
Yeah.
So this is really the secret. The secret is to listen to your peers that are younger than you. And it works for me.
Wow. And that's how you get new investments and new ideas in place then.
Yeah.
So it drew a parallel, what you said to the reporter. And there's a friend of mine who sends very nice quotes, and you might like this, so I'm just throwing it in. He sent me a card which said, the honeybee is so structured that the body size is way bigger and the wingspan is really small. So aerodynamically, it cannot fly, but it doesn't know that, so it does anyways. So similar to the students, they don't know that they can't fly, so it's
Yeah.
perfect, you do it anyways. So just my
Amazing.
last question, Oded, and this is something I ask every guest because it's so inspiring to hear how you think about this idea. So what does good garbage mean to you, in the sense that, and I know you're working in that field as well, but how does that seem to you in the future? What would the idea of good garbage mean to you?
Good garbage is simply a stream of raw material for something.
Wow, it's just mimicking nature.
Yeah,
That's wonderful.
absolutely.
Thank you so much, Oded. This was wonderful, but I'm going to also let you, in case there is anything else you want to add for the people who will be listening in, if there are any directions, any recommendations, would love to hear.
So I'll just say that I really enjoyed again, to have a discussion with you, and I think that what you're doing in Good Garbage is really important. It's important for the world. It's really important for the future of us, of our children, grandchildren, and really keep up the good work.
Thank you, Oded, and thank you from the bottom of my heart. And I look forward to more and more conversations with you.